When we talk about plumbing in a house, we're looking at two different parts of the system, water supply and wastewater. Water supply brings the water into the house. After that water gets used, the wastewater system takes it out of the house. And the water supply system has water coming in because of water pressure. Wastewater works differently. It flows out purely due to gravity. And we're talking right now about water supply, so that comes in because of water pressure. I captured this picture out of a kid's book. I find that kids' books often do a good job of showing you pictures of how things work. So here is a water bucket with 3 holes drilled in it. And what this picture is showing us is that water is heavy, and the deeper you are in the bucket, the greater the water pressure. And so the hole at the top of the bucket doesn't have as much water pressure. The hole at the very bottom of the bucket has the most water pressure, and that water is squirting out harder. That's why that water pressure is why in a city water system you'll find reservoirs up high. So water pressure comes from a tank or a reservoir being up above where the faucets are, and the water pressure from the weight of the water pressing the water out. In cities, you find water in tanks. This picture in the upper left is in Portland, classic water tank. This picture in the lower left is from Manhattan in New York City, where those water tanks are classic icons of the skyline. When you look at water supply sources, like in Eugene and Springfield, you'll see tanks and reservoirs, and you'll notice when you look at a map and you see where are those reservoirs, this is a map of Eugene, you'll see that those reservoirs are at high points. And you can figure out just how much water pressure you get from just how much height. It happens that the weight of the water causes 0.43 of a pound per square inch, a PSI, for every foot of height. What does that mean? Imagine that this tube here were a 1-inch square tube. So it's 1 inch square. That means it's a square inch at the bottom. And if you put 1 foot of water in that 1-inch square tube, that 1 foot of water would weigh 0.43 of a pound. If you put 2 feet of water in that tube, it would weigh twice as much. Let's see, 2 times 0.43. 2 feet of water would weigh 0.86 pounds. If you put 10 feet of water in that 1-inch square tube, it would weigh 4.3 pounds. If you put 100 feet of tube filled with water, 100 feet times 0.43, that tube would weigh 43.3 pounds. And so the pressure at the bottom of that 1-inch by 1-inch square tube, the pressure would be 43 pounds per square inch. Well, the building code for houses requires that we have water pressure of at least 40 psi. So that tells us that it must be that our reservoirs and tanks are at least 40 feet above where our faucets are. If you're not on city water, maybe you have your own well, then you get your water pressure from a pressure tank. There's a pump. Well, let's see. In the tank is part air, part water. And the pump pumps water into the tank. And as the tank fills up with water, that squeezes that air cushion. That air has no place to go, so it gets compressed. In other words, it has higher pressure. And then when you turn on your faucet, the water comes out. And there's a pressure switch here on the line that senses what the pressure is, and when the pressure drops below a certain psi, it switches on the pump, and the pump pumps more water in. And I don't know if you've ever lived in a place with a well and a water tank, but when these things get waterlogged or something goes wrong, it's frustrating. All right, so in a water supply system, it moves like branches of a tree, or maybe streams in a stream system. Water comes in a bigger pipe, then feeds out through slightly smaller pipes, and then goes out through even smaller pipes. Let's look at some vocabulary. Potable water is water that's safe for humans to drink. Domestic water is water that's used in fixtures, and a fixture is a fixed thing that has water flowing through it. So domestic water is used in fixtures like toilets, faucets, showers, washing machines, dishwashers. It's usually in a house, but a domestic system doesn't have to be in a house. It could be in a hotel or a business. Anything that uses these kinds of fixtures is domestic water. And in our houses, we have usually a water heater that heats the water and stores it until we need it and we turn on the faucet. Or we might have one of these tankless water heaters in the wall. In our houses, in residential buildings, let's say you have a water heater. This is plumbed as a one-way system. So the water sits in the water heater and in the pipes, and it just sits there and waits. And when you turn on your hot water faucet, water runs out of the pipe and it's cooled off. So as you know, at first, cold water comes out of the faucet, and you wait until the water that's been heated runs through. Well, that's a one-way trip. And that water runs through and down into the wastewater system, and then more water comes into your water heater and it has to get heated up. A commercial building doesn't work like that. A commercial building has its hot water system running in a loop. I don't know if you've ever been in a motel or a hotel. When you turn on a faucet in the bathroom or you turn on the shower, and hot water always comes out, and it comes out pretty quickly. I mean, pretty soon. You don't have to wait long. And that's because of how commercial hot water systems operate. They are in loops, and this water flows through the pipe back to the water heater again. Commercial water temperatures are higher than residential water temperatures. Now, in a domestic water system, there is a short length of pipe up above the valve called an air chamber. And you could picture maybe that pressure tank that we looked at when we talked about well water. Air is compressible. Water is not compressible. Air is compressible. And so this is like a little, I don't know, a spring, let's say, a cushion. And its purpose is to prevent water hammer. We don't have water hammer in modern houses, so you might not be familiar with it, but if you've ever been in an old house, you might be familiar with water hammer. It happens when you turn off the faucet and there's a sudden drop in pressure, drop in velocity, and a spike in pressure, and the pipes start banging. It's like there's a giant in there with a sledgehammer clanging and clanging and clanging. It sends shock waves through the pipes, and it can actually cause them to break. So that's why we put these air chambers, these air cushions in our plumbing systems now. In a house that's framed, like here's some wood studs, we put pipes inside the wall, and we do the plumbing rough-in right after the framing has happened and before we put the finished surface on, so before the sheetrock and stuff goes on. And we saw this same idea when we looked at electrical wiring. The framing goes in, the electrician comes in and roughs in the wiring, the plumber comes in and roughs in the piping. In the building code, there are rules about where notches and holes have to go. So if you go cutting holes in these beams and joists too close to the edge or too close together, you will weaken that beam or that joist, and then the thing could crack and everything could fall down. So the code is very specific about where and how far apart you can put these things. And I put some notes in the bottom of this slide out of our book if you want to read about that.